Hi everyone, welcome back. In this video, we are going to look at denoising 2D, 3D images, multi-channel images using our deep learning, favorite deep learning based approach called Noise2Void. And I talked about it in the last couple of videos, so I definitely recommend you to go back to video number 292, 293, the last couple of videos to get some idea about what we were talking, right? I mean, that provides some foundation into understanding what's going to happen in this tutorial, because otherwise you may have some gaps in your knowledge. Okay, with that information, let's go ahead and jump in, but I would like to request you, as usual, to hit the subscribe button so you get notified as soon as a new video gets uploaded. And also, while you're there, if you're feeling extra generous, hit the thanks button. Okay, let's go ahead and jump in now. And the image we are going to be denoising is the one that you see on the screen. Initially, we'll only focus on the single image right there, but then I'll also walk you through the process of the Z stack, like segmenting this entire Z stack of these images. Again, this image has two channels. This is not a black and white, this is not a RGB image. This is actually a grayscale image where we applied false color to each channel, the green channel and the red channel. Again, for microscopists, you probably think I'm explaining basics, but if you're not a microscopist, then this can be a new concept to you. So each image is a grayscale image. Each image is a grayscale image, but it has been falsely colored using appropriate colors right there. And the colors are mixed, so you get different information. Okay, so this is showing mitosis right there. Many of these cells like dividing, as you can see, one right here, one right there. That is a quick information I would like to provide. And this is again a confocal image collected using a ZEISS microscope, which means the file format in this case is .czi. Yeah. But if you're working on other microscopes, for example, a Leica, Olympus, Nikon, it doesn't matter what microscope you're using to collect your images. Oftentimes you have two choices. One, save it in its native format, which I always recommend. The other, export it as a TIFF file, in which case all the channels are merged and you get like an RGB image. So oftentimes you'll end up working with native images. So for CZI, to read these images, there is a library called CZI file. I know for Olympus there is something called OIF file or something similar. No matter what proprietary format, you will find a Python library to read those images. And the process is going to be the same. If they are TIFF or PNG or JPEG, then it's pretty easy. Just use scikit-image to go ahead and read these images. So, okay, enough background. Now let's go ahead and jump into the code. Like I mentioned, I am going to start with a 2D case, and then we can expand that to 3D. I want to make sure you understand the 2D part first. So I have some description over there. Again, I went through some of this in the last video. The first thing we need to ensure for Noise2Void, at least based on their current documentation as of late October 2022, is that we need to install TensorFlow 2.4. So that's what I have done, and I've already done that to save our time right here. And after that's done, you must restart the runtime. I have done it. And now let's go ahead and install Noise2Void. It's again pip install N2V. This should be pretty fast. That's why I haven't done this before hitting the record button. And once that's done, we are going to install CZI file. Again, this is where it's up to you. Now, if you have Olympus file, then that I believe that's, yeah, OIF file. So whatever the appropriate library is, go ahead and install it. And this is helping us read the image if it's in a proprietary format. Again, you don't have to do any of that if you have non-proprietary format. Although if you have TIFF files, if you're working with those, you can use scikit-image. And scikit-image in the backend uses something called TIFF file library, or you can directly install TIFF file. Okay. Now that you know all of that information, let's go ahead and look at what versions we have. So our TensorFlow is 2.4 and our Noise2Void is 0.3.1. Moving on down, there are a couple of lines that we can probably delete, like URL lib, import zip file, and these lines, because we are only going to use the pyplot and all the N2V libraries right there. Of course, we're going to plot the history after training, NumPy and N2V for model, and configure it to create the configuration file. We need this N2V config, and so all these libraries hopefully Makes sense. I said we can delete URL lib and zip file because I copied this from the Noise2Void example files, and they downloaded an example file from some URL, so they needed these two. We don't. Okay, moving down. Training. Let's understand. So in our case, we're going to use the CZI file, like I already mentioned. I uploaded the file that I showed you, like this single file, into my Google Drive, onto my Google Drive, and here is the direct link. Now let's understand the CZI file. Before we load all the images and all that stuff, let's first understand what's going on here. So I am going to use czifile.imread to read this, and I will be printing this. Let's go ahead and run all of these so you can see exactly what happens. Okay, so when you read this file, in this case, these are the dimensions, 1, 1, 2, 1, and so on. But we need to get all of this into this format, Y, X, and C. Yeah, just like in the last video, you have width, height, and your number of channels. So we need to get this image. And why do we have all this extra stuff? Well, this is number of scenes, this is the Z stack, this is number of channels, and this is number of something else I forgot, and so on. We don't need all of that. All we need is these two for the two green and red channels, and these two for X and Y. So that's exactly what I'm doing right there. And as you can see, the shape from this went to 587, 587, and then I swapped the axes of these two from here all the way to the last, and finally at the end of this, my test image has this format. Okay, now that you understand this, let's go down and actually load our data and convert that into float32 format, because that's exactly what's required for our training. I've written a function here called load images. And all it's doing is, by the way, when you use DataGen, the input that goes into the training, into the patches, because we load a whole bunch of images, divide them into patches of the same size, let's say 64 by 64, and then we provide that as input to the network, right? So for that, to divide that patches, we need a list of NumPy arrays. So that's exactly what I'm creating here. So I start by creating an empty list, and then I walk through whatever the directory path that I'm going to provide. And in there, I'm going to use czifile.imread and read each image right there and extract only the channels. These are nothing but the steps that we just saw up here, right? Extract the channels that we care about and move the axis to the last, and then convert my image to float32 using my scikit image as float32, and expand the dimensions by adding another axis at the front, and append the list, read the next image, do the same, read the next image, do the same. So let's go ahead and define the function. That's just defining a function. We need to call that down here, and my base directory under CZI images folder, I'm reading all CZI images. Currently I only have one, but you can have many CZI images. And I'm calling my load function, load images right there function with this path, and let's go ahead and do that. And now I have all my images captured as a list. Well, only one image in this case captured as a list. So let's go ahead and understand the dimensions. So I have one image, that's it. You can have multiple, like I mentioned, and that dimensions of that image is 1 by 587 by 587 by 2, and it's float32. Okay, let's go ahead and look at this because let's drop that dimension and let's look at the 0th or first channel right there and plot it down here, and there you go. So that's how the image looks like. Basically, that's nothing but this, except I'm only looking at the red channel. Yeah, you see these right there and these two right here. That's exactly what you see down here. And if you plot the 0th one, then that would be the green channel, obviously. Yeah. So now we know the image is loaded. Okay. The rest of it, we saw it in the last tutorial, so I'm not going to spend a lot of time. So we are using our data gen from N2V to create a data generator. And again, this data generator can be used to read images, to create patches, and to do a multiple different types of things. That's what we are using that. That's why we're defining that object right now. And now let's define a patch size of 64 because I want my large images to be divided into patches of 64 by 64. And again, if you have I don't know, 500 images and you want to divide all of those into 64 by 64, this is an easy way. Datagen.generate patches from list, and it goes through every image in your list and divides them into patches and adds everything into one nice data set or NumPy array. Okay, so let's define our patch size as 64 and datagen generate patches. So my input image is now divided into 648 patches, each patch of size 64 by 64 by 2. Again, if this is a color image, this would be 64 by 64 by 3, right? You have RGB channels. We did that in the last tutorial. Okay, I'm printing the patches again, and now let's split our patches. So I have 648. I'm taking 80% of my patches and assigning them to train, and the remaining 20% as validation right there. And I call my train just X. The validation is X_val. And let's go ahead and print the data types, so you know, okay, now we have 518 images available for training, ready for training, and 130 images ready for validation. Okay, now let's go ahead and pick the first train patch and the validation patch just for quick visualization. But now we are almost ready for our training. We need to define all the parameters that's required for training, which is how many epochs and what type of network do you want to use. Obviously, we have to define our model. Like, do we want UNet? If so, like, what is the depth and all that stuff? So that is done down here. And I am defining my batch size as 32. And then my unit kernel size as 3, like each kernel is 3 by 3. My first number of filters for my unit is 64. You can control. This is how you control how your unit architecture looks like, and all the other required parameters are down here. And training epochs, I trained something. I mean, my original one for 150 epochs. But in the interest of time, let's go ahead and change this to 50 for now. And define the config. There you go. And now let's come down and do the training. This was my original training right there. And we can, let's do it live. I mean, I thought of actually loading something that's already saved. And I call this N2V 2D multi-channel. Let me just change this to 50 epochs so we know that this is different. Yeah, so it actually saves this as a different file. So that's my model name. And now let's go ahead and train our model. And once this is trained, in fact, the last time when I trained it, you can see how nicely it's settling down, and it's a pretty good training. And with, I think even with 20 epochs or 50 epochs, we're not bad. It's not, the model is not getting any better after 50, maybe slightly better, but with 50 epochs, we should be fine. So let's look at how the denoised image looks like after 50 seconds. Literally, each epoch is a second, so after 50 seconds. Let me go ahead and pause the video and continue as soon as this is done. Okay, so it's done a few seconds later, and it stored the weights as weights best .h5, and again it stores it under your models directory. Again, we saw that in the last tutorial, so let's not waste our time doing that. So let's replot it. Let me close this plot from before, and let's replot this. Not bad, very similar to what we got, I got the last time. So I'm happy with that, and now it's ready. The model is there. So if I go here, if I go to my models, I should have N2V multi-channel 50 epochs, and that can be used. These weights best can be used for my denoising. That's exactly what we'll be using as we go down. So let me close that part. So here, this part you can copy into a different file. I just want a single file to share with you, so I copied everything into one. But let's go ahead and import our libraries. All we need is n2v.models n2v, numpy to handle our arrays, pyplot, and imread to read your images. But we're not going to use this imread because it's a CZI file. We're going to use our own, so you may as well remove that. And also the last line, we may as well remove it because we have a multi-channel data set that cannot be saved using this process. Okay, so now what model do we need to open? I forgot, I added underscore 50 epochs, right? So where is it? Yeah, underscore 50 epochs. So let's do that. 50 epochs, and it's in the models. Yeah, so when I hit run, it should be able to load that. Yeah, it did load it. Now let's go down and do the prediction. First thing first, we need to load the image. So I'm using czifile.imread just like before, and I'm doing the same pre-processing steps right here that we have done before to get the image ready to the right dimensions. And if you wonder what the right dimensions are, there you go. It's 587 by 587 by 2, and the floating, it's a float type 32. Now it's just model.predict, and this is YXC format. So let's go ahead and predict the model. You may see this part to be exactly similar to the last tutorial, and I was experimenting with different color maps, so let me delete that. I don't want you to be distracted. Okay, so let's go ahead and plot this, and there you go. So that's your input image. You can change this to greens if you or red if you want to see this in red. But anyway, this, I thought this makes this conveys better via this screen recording. Okay, and you can adjust the brightness parameters on this right-hand side image to actually get a true representation of the denoised image. Okay, there you go. So that's your input noisy image. That's your nicely cleaned denoised image. And now how do you save this? Like, okay, you have a 2-channel image. This is a scientific image. And I recommend a library called, a format called OME-TIFF. I believe it stands for Open Microscopy Environment TIFF file, and it can actually store multi-dimensional images. If you have time series 3D multi-channel data sets, this can be a good way, a universal way of, or an easy way of saving your images, and that can be opened using programs like ImageJ, or any other scientific imaging program should be able to open that file. So if you are curious about how to do that, then the way I recommend is go ahead and pip install Appear OME-TIFF library. Yeah, our team did this. So proud of it. So Appear OME-TIFF library. Once you install that library, you're going to import input-output module like IO. And what is the shape of our 587 by 587 by 2, right? So we need to get this into a shape of the time, Z, channel, X, Y, and that's what these lines do. And once you get that, okay, there is only one time in this time series. This is not a Z stack, and there are 2 channels, 587, 587, and I can just write it wherever. And now you can open it using ImageJ, whatever scientific program. Okay, now let's switch to 3D. I'm not gonna go through 3D like at this depth. I'll show you where the key differences are. I'm going to share both files with you, so of course you can play with them in your own time. Same thing, we installed the TensorFlow right there, and then we go down, we install Noise2Void, and then we install our CZI file. Again, we need to handle these CZI images and then load all the appropriate libraries. And same thing for my CZI file, I need to get it into the right shape. So as you can see, when I opened it initially, it showed me 1, 1, 2, 23, 587, 587, 1. If I actually open that file in my ZEISS software, you can see I have 23 Z positions, 1 to 23 Z positions, and I have 2 channels right there. And if I go down to info, it gives me more information in terms of, okay, it's 23 slices, 2 channels, and that's the pixel size, and 587 by 587. It's an 8-bit image, and it's collected on an Axio observer, ZEISS Axio, all the information. You don't need all of that. All we need to know is that, okay, it's 2 channels, 23Z, 587 by 587. So we need to get that into the right format. What is the right format? It's ZYXC. So 23YXC. That's it. We are done. And the next step is load your images. Again, if you have multiple images, exactly same as the 2D case, except we need to be mindful about ZYXC, right? And converting into float 32. Loaded the image, and there you go. So that's my input size: 1, 23, 587, 587, 2. And here is one of the slices that I plotted. And now comes the data gen part. We need to divide this image into different patches. It is a 3D image, so the patch size is going to be 3D. So I just defined my XY patch size as 64, my patch size in Z as 8. So the actual patch shape is going to be 8 by 64 by 64 patch size. So if I divide my image, the 3D image that I have, into these patch sizes, I have 1,296 patches, each of size 8 by 64 by 64 in physical dimensions and 2 channels. So we are a truly multi-dimensional image, as you can see. Yeah. So that is my patches, and I divide those 1,296 into 80% for training, 20% for validation, and there's the shape, like 1,000 images for training, 260 for validation. And now here is one of the slices, patches that you can see. And how do you configure? Exactly same as before, except in this case your patch shape is going to be 3 dimensions. That's it. That's the only difference. Patch size Z, patch size your in Z size, and Y and X. Other than that, everything else is exactly the same. I don't think there is anything else to change over there. In fact, I haven't changed anything, and I trained this only for 5 epochs because this is slow. Yeah, slower compared to my 2D. So I trained it only for 5 epochs, as you can see, all the 5 epochs right there. And when I go down, I mean, it helps if you have a lot more data, but there you go. That's how the training went. And I did the segmentation part is almost identical. So you load the model and you get your image to the right dimensions. And there you go. The right dimensions is 23 by 587 by 587 by 2. You supply that to your model.predict with a tag called axis is ZYXC. So it knows why it is 4 dimensions right there instead of only 3. And your model gets predicted. And there you go. I'm just plotting one of the slices from my 3D volume. And this is how it looks like. And if you want, you can extend this by saving this final result into an OME TIFF library and doing exactly the same as I showed you the last time. I mean, with the 2D case. So now we have 1T but 23Z. Previously we had only 1, right? So all of these, and go ahead and save it, open it in ImageJ or any other scientific image processing software. Okay, there you go. I should end my video. I don't want this to be any longer or boring than it needs to be. I hope you really learned something in the last 3 tutorials, which is Noise2Void is great for scientific images and also for non-scientific images. Go ahead and try it out. It's a great deep learning based approach that doesn't require you to have ground truth. It works only on the training images. So that is the best part of this. If you have actual ground truth, like for every noisy image, you have a denoised image, like a clean image, then noise to noise is probably a better approach because you have more information about your image. So other approaches may actually work equally, if not better. But if you have no other alternative, only noisy images, this is an amazing approach. Okay, guys, thank you very much. Hit the subscribe button.